Okay, young man, I'm going to teach you how to maths. I think where we last left off was that we just need to talk about questions from 5. I think we've covered everything from 6 and 7. So I just need to check in on the 3 questions from 5. So here they are, this one, and this one. Okay. And I'm going to go through each one with you, and you can check against your work. Okay. So again, reminder of the instructions. We have to find the non-permissible values of theta and try to simplify the thing. Basically, that's what double I is asking for. Okay. So for 5b, here it is. And what I'm going to start with is, okay, so for part I, you're thinking about, what are the values of theta that would make it non-permissible? Non-permissible usually means like it's out of the domain, dividing by 0, stuff like that, okay? So in this case, there's kind of only one domain going on here that we're concerned about, and it's in the denominator. So if cosine of theta is equal to 0, then that's no good, right? And I'll set a bound, say theta is between 2 pi and 0, okay? Because obviously if we let this to be infinity, there's an infinite number of possible thetas to set cosine equal to 0 by coterminal angles. So here I'm thinking about, okay, how do I set cosine to 0? Cosine is equal to 0 when there's no height, right? So that means that at 0 degrees, the terminal arm has no height. At 90 degrees, sorry, when I say height, I mean horizontal distance. Okay, at 0 degrees, cosine has horizontal distance of positive 1. At 90 degrees, there's no horizontal distance, looking at the pink terminal arm. And then looking at 180 degrees, the terminal arm, you can see that has a horizontal distance of -1, but has no height, right? And then finally, at 270 degrees, cosine here we know to be 0. Why? Because there's no horizontal distance, okay? And that's kind of how I think about it. Think about it as horizontal distance. So in which one of these cardinal arms is the horizontal distance of the terminal arm from the y-axis equal to 0? Well, it would have to be 90 degrees and 270 degrees, right? Within the bound of this. So I can write that as theta cannot equal, here we say 90 degrees is the same thing as half pi, and then 3 pi over 2. That would be the 270 degrees, okay? Anytime you have -1, 0, usually you're always going to be dealing with something on the cardinal lines, okay? Then for 2, we need to simplify this. The easiest thing that I see at the top is like if you kind of think about grouping just this part, right? Like imagine if we introduced a bracket, then we kind of know that right away this piece would go to 1, right? By the Pythagorean identity, right? So if that were the case, 1 minus 1 is 0, right? So then you have 0 is over cosine of theta. So this thing just simplifies to 0. Okay, so that takes care of 5b. Again, I know it's kind of awkward that it simplifies to just a number, but how you say, we are inspecting the non-permissible values on the original function. So I understand that irregardless of what we plug in for theta, we should always get 0. That is true. However, keep in mind that, again, the non-permissible values is based on the original function, okay? Not the simplified function. Because obviously there's no domain and range here for just 0, right? Yeah. Okay, cool. Next one. This is the one where we have to be a little more careful because once we perform some algebra, it's nice, as a good habit, to double check the non-permissible values in the original function and in the simplified function, okay? And I'll show you what that means. So for I, maybe we can think, okay, just looking at each individual fraction, looking at the first one, how can I set the denominator equal to 0? Because if I can find that theta value that sets it equal to 0, that means I need to make that theta non-permissible, okay? So I'm going to kind of do the opposite, which is I am going to set this equal to 0, okay, which is obviously not allowed, right? Because if this whole thing is equal to 0, then we're doomed. But if I set it equal to 0 and later say, don't let theta be this specific value, then we're in good shape, okay? So here we can see that this is sine of theta is equal to -1. And then when is sine equal to -1? Go back to our Cartesian plane. And then here we can think, you know what, sine is always like heights, right? So the y value of the terminal arm. And since the radius of this unit circle is 1, it's got to be at like one of these maximal points, right? Because notice how if you had a terminal arm with radius 1, the height here would never be able to go to 1, right? It has to be on one of the cardinal directions, okay? So I'm going to pick this one because that is, first of all, the vertical is of length 1, and it's pointing in the negative direction, so -1. Then we can deduce that theta is equal to, I will write it in radians. Okay? So now that we found the theta that makes the denominator equal to 0, then we need to know for sure that, okay, remember, theta, therefore, theta cannot equal 3 pi over 2, okay? Because if that's the case, it's no good, right? And what I'm going to do is let you try for this one. It's going to be essentially almost identical, okay? I think the only difference here is that you need theta not equal to pi over 2, okay? But I'll leave that as practice for you. All right, so far our non-permissible values is these two things, okay? Again, given the caveat of we're checking from 0 to 2 pi, okay? Yeah, so now comes the algebra because we need to simplify this thing. So what I'm thinking about is that, you know what, I have two fractions essentially, right? So if I have two fractions, how do I add fractions? Well, I need a common denominator, right? And this is kind of the motivation. So think about like if you have the case of 3 over 7 is added to, I don't know, like 1/2, right? The easiest way to make a common denominator is to just multiply the two numbers together in the base. So then you can say, okay, 2 times 7, so this is going to be times 2 times 2. I do times 2 to both sides because obviously you need an equivalent fraction, right? That'd be 6 over 14 plus 7 over 14, and then yada yada, you get the idea, okay? So obviously that's an extremely elementary example, but that's essentially what you're going to do here, right? Notice how for that example, I cross-multiplied essentially, okay? And then the new denominator was just the product of the two bottom denominators. Okay? We use the same idea. So I'm going to cross-multiply 1 minus sine multiplied to cosine. So that's going to be cos theta minus sine theta multiplied to cos theta, okay? And then if I cross-multiply this, then it's going to be cos of theta plus sine theta cos theta, okay? You probably had a moment where you're worried about this term, but fear not, they cancel out, right? And of course, they have the same denominators, which is 1 plus sine theta times 1 minus sine theta, okay? I'll leave it as an exercise for you to multiply those two things, but you get 1 minus sine squared theta. Okay, and here you can notice that the denominator has, how you say, you can use an identity. You can use a Pythagorean identity, right? The one specifically that I think about is sine squared theta plus cos squared theta is equal to 1. What do we have here? We have 1 minus sine squared. So I'm going to take this term and move it to the other side. So then what are you left with? Cos squared theta is equal to 1 minus sine squared theta. Okay? And that's great because now we can replace all of this with just a single trig ratio squared, which is ideal. Okay, so let me clean that up for us. Here in the numerators, let's add all of this up. We can add them because now they have a common denominator. So how many coses are there? Well, there's a positive cos, positive cos. Okay, fantastic. So I have 2 cos of theta. And then over here, these two terms, that's a minus sine cos, and that's a plus sine cos, right? And since they're added, you can think about -1 is added to +1, right? That should be 0. Okay, so they cancel out. So that means all I'm left with then is we identified earlier that 1 minus sine squared is the same thing as just cos squared theta, right? And I think the last step looks pretty straightforward. You just need to cancel out the 2 coses, and we can do that because this is multiplying, okay? If there was like 2 plus cos on the top, you're screwed, okay? You must have multiplication. So then now you have 2 over cos theta, and I think you can recognize this as 2 secant of theta. And I think you're done there, okay? Now might be a good time to just again reflect on our domain, which is to say, okay, at some point we got to here, right? Which is the same thing as this. Notice how near the last step we can think about, okay, can I have cosine of theta equal to 0? No, I can't, right? So that means we also have to take that into account. So it's not only do you have to check the original domain and range for non-permissibles, but you should also check like your final simplified form, okay? It's really annoying, but you really only have to do it, no matter how complicated the question is, you only have to do it twice. Once in the original question, and once more at the end when you've simplified it, okay? So technically, I'm looking at the non-permissible values of secant, right? But to make life easier, it's easier to see it as 2 over cos of theta, in my opinion, okay? So that means if cosine is of theta is equal to 0, we're doomed. Okay, cos is equal to 0 at pi over 2 and 3 pi over 2. Okay, and luckily enough, that matches exactly what we had earlier. So we're in good shape. Okay, again, just best practice to make that check. Almost in every problem I've seen, there shouldn't be a new non-permissible value introduced, but it's good practice, okay? Especially when you do composite functions, because then it'll definitely change that. And then now we can take a look at 5D. And here we can start with, start with the non-permissible values, okay? Looking at the top, this is kind of like 1 over sine theta, right? All divided by, you can think as cos over sine, sine over cos. Okay. I'm doing this because, you know, technically you have like a fraction here and here and here, right? So anytime you have a fraction, you have an opportunity to divide by 0. So you should check that out, right? And I think I left a note for you here, where because you're adding 2 things, you know, if they're both zeros, 0 plus 0 is 0, so that's doomed. You know, if they're of opposite signs, then also doomed, right? So we'll inspect those later, but let's check out all of these first, and I'm pretty sure there's going to be a lot of overlap. So looking at just the top part, the numerator 1 over sine. Sine of theta, if it equals to 0, is doomed, so that means that theta can, here, I should categorize this. This part here implies that theta cannot equal, okay, when is sine 0? So that's when the terminal arms are laying flat, right? Perfectly flat. That only happens at 0 degrees and pi, right? Because those are super flat. So that also takes care of the domain here, right? Because that's also a division of sine. Sine is in the denominator. If sine of theta is equal to 0, yada yada, same thing, okay? The other one that's new is this. So we have sine of theta over cos of theta. If this cosine of theta is equal to 0, life is not good, right? And you know, we've seen this question already, so I'll move ahead. We cannot let theta equal pi over 2, nor can we let it equal 3 pi over 2, okay? All right, sweet. So now that we've got this much down, we need to maybe take a look at the cases. Okay, so all of this here was for this. Okay, now I'm going to take a look back at this original function, and I'm going to talk about the two parts where if cotan and tan were equal to 1 and negative 1, and vice versa, you can have obviously the case of 0, right? So let's think about it. If there was a way, like a single theta, such that it would cause cotan to equal positive 1, and using the same theta cause tan to equal negative 1, then that is no bueno, right? If that is possible, we need to exclude that special theta, okay? The one I'm going to start with actually is, let's see if we can use one theta value, okay, and set this thing to 0 and this thing to 0, okay? Because 0 plus 0 is 0. When can cotan equal 0? Well, cotan is cos over sine. So if I set this thing equal to 0, cos of theta over sine theta is equal to 0. Well, if the numerator is equal to 0, then we're in good shape, right? Okay, cool. So what are those angles? Well, cosine can equal 0 at pi over 2 and 3 pi over 2. Okay? So because the moment that cosine is equal to 0, 0 divided by anything is 0, right? So that means here we have pi over 2 and 3 pi over 2 that are potential to exclude. Now, we already are excluding them, but let's imagine that we did this first before we inspected this, right? Just for completeness, okay? And then we can kind of think about tan. If tan of the same theta is equal to 0, then it's doomed, okay? So if I plugged tan of theta in for theta is equal to pi over 2, let's see what happens, okay? So if we did that, pi over 2 into here, oh no, we can't even do that, right? These two values cannot even go into cosine. We can't even test for tan because you're already dividing by 0, okay? So that means what? It means that the case of 0 plus 0 cannot be satisfied, right? There's no single theta value ever, no matter what coterminal angle you choose, no matter how long you search, never, ever, ever will a single theta that can go into cotan and tan for them both to be equal to 0, okay? Which is kind of unfortunate. The reason is because you can think about it, if cotan had a 0 over 1, well, what is tan? Tan is the reciprocal, right? So then the reciprocal would be 1 over 0. Oh, you cannot do this, right? Because you're dividing by 0. So no matter how hard you try, and same for tan. Imagine tan, we found a value where it's 0 over 1. And what is cotan? Cotan is the reciprocal, right? So then you have 1 over 0. Oh, GG. You can't divide by 0, right? So that means the case of 0 plus 0 can never happen. Okay, great. So the other one is if we can have either cotan is equal to positive 1 and tan is equal to negative 1, or vice versa, if cotan is equal to minus 1 or tan is equal to positive 1. If we can find a single theta, okay, that's the important part, it's a single theta that can generate both of them for each tan and cotan, then we found another value to exclude, okay? So let's see what that might be. Let's think about how can we set cotan to be negative, okay? Let's see. So cotan and tan share the same quadrants in which it is negative, right? Okay. So that means tan is positive in quadrant 1 and quadrant 2. So that means cotan is minus in cotan and tan is negative in quadrant 2 and quadrant 4. Okay. So I think about for something to equal 1, right? So let's look at cotan specifically first. For something to equal 1, you need the same thing on the top and the bottom, right? Well, what is the ratio of cotan? Cotan is the adjacent over the opposite. So if this is the angle of reference, it's these two sides, right? And what do we specifically require? We require that the adjacent side and the opposite side must be exactly the same, okay? Because if they're not exactly the same, we can't generate 1, okay? To generate -1, obviously notice how in this quadrant the adjacent side is negative, right? And then the opposite side is positive. So that means that adjacent would be negative, opposite would be positive. So you're guaranteed to have a -1, so long as obviously the values in the box are the same, okay? So now that we understand what we're looking for, think about a special triangle that has opposite and adjacent the same. It has to be the 45, 45, 90 triangle, right? And we know that that means this reference angle must be 45 degrees. Okay, cool. So knowing this reference angle, now we can talk about what those theta values are, right? After we check tan. Okay, so a potential candidate is going to be, what is it called? 90 degrees and then 45 more, or you can think 180 minus 45 degrees. Again, I'm looking for this angle in standard position, okay? Now, what about tan? Okay, so we know that cotan of theta is equal to -1. What about tan? Tan of theta is equal to the opposite over the adjacent, right? Okay, in this case, the opposite and the adjacent are the same things, except they differ in signs, right? So they are the same things, but the opposite side is positive now, and the adjacent side is negative. Adjacent is negative. Okay? So what is this equal to? Well, if the numerator and denominator are the same, you're always going to get 1. Since you're doing a positive divided by a negative, you're going to get -1. Okay? So what's interesting is you can never use a theta value to make cotan and tan equal different values of 1. Okay? You can't have a theta that makes cotan -1. You can't have one that makes tan +1, right? And vice versa. So that means this case will never happen as well. So I'll leave as an exercise for you to check this one. Okay, pretty much the same idea, but you can do this inspection of signs to kind of make firm in your mind why it doesn't work. Okay, so we can't get cotan and tan to both equal 0. We can't get cotan and tan to equal different values, right? Like opposite values, if you will. So then in that case, these are the only restrictions. Okay. Now the last part is to just see if we can simplify it. A little bit anticlimactic, right? So much work, and you know, it was basically done here, right? But you must make firm this in your head, okay? Or else it's like you will not be sure. You can only be sure retroactively. Okay, so looking at the bottom, what we can do is, well, there's a bunch of things we can do. I'm going to choose not to use a Pythagorean identity because I don't have any squareds. Like I don't have cotan squared or tan squared, right? So there's really only two things I would think is plausible. And the first is that what you can do is you can multiply the denominator by cotan minus tan. Then you could make cotan squared minus tan squared. Yes, that's possible. Don't forget to do the same thing to the top. The other is you just simply decompose it into sines and cosines and then collect like terms, okay? So obviously the latter is a lot easier, okay? So let's proceed with that. And if I have time, I'll also show you the harder way of solving this. So looking at the, my example in the top there, looks like in the big denominator, I need a common denominator of sine cos, right? Because sine times cos, that should get us the common denominator. Okay, so I'll write that in first. And to be honest, you can try simplifying it first. You can pause the video, try simplifying it yourself, and then come back and check my steps. Okay, done. So we notice that it all simplifies to just cos of theta. And just as a sanity check, notice how the simplified form of cos theta has no domain restrictions, right? But that doesn't mean that you just forget about these, okay? Forget about these, you can't, okay? So though the final simplified form does not have any restrictions, remember, the non-permissible values is based off of the original question. So don't forget about them, okay? It's not as if it's like, haha, this thing is cosine. I don't need any of these anymore. No, 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 no. You must keep, okay? You must keep. All right, cool. Yeah, let's see if I can fit really quick. I'll just show you what I had in mind as an alternative solution. Let's see if I can move everything up a bit. We were originally given cosecant. Okay. And what I'm going to do is, remember, this thing is not an equation, it's an expression. There's no equal sign, right? So there's really very limited things we can do. We can multiply by 1, we can add 0, we can raise to the power of 1, right? That's about it. So what I'm going to do is I'm going to multiply by 1 in a very special way, which is cotan of theta minus tan of theta all over cotan of theta minus theta, tan of theta, okay? Notice how I have the same thing top and bottom. So therefore, it should equal 1, okay? It is equal to 1. So now if I multiply it out, the numerator is cosecant of theta times cotan. I'll come back to simplify this in a moment. I'm just going to write it out first. And then the denominator, that's really interesting. It's a difference of squares multiplied together, right? So difference of squares have that property where, you know, a plus b multiplied to b, a minus b is equal to a squared minus b squared. Okay, so that means I just need to square the cotan minus the square of the tan. And then the numerator, that's 1 over sine times cos over sine. So cos sine squared minus, okay, cosecant is 1 over sine. Tan is sine over cos. Okay, so then that means you're left with just cos theta. Because you're left with cos on the bottom. Yeah, because the signs cancel out, right? Okay, and then this is the numerator, okay? And then the denominator, I would probably use some sort of Pythagorean identity. So here's where it gets really messy, and why I didn't recommend this is because if you take a look at the Pythagorean identity for tan squared of theta, I believe it is 1n secant, right? But cotan is 1n cosecant. So that's no bueno, right? Because now you have a bunch of like different trig ratios, okay? It can be resolved. Okay, as long as you hit your head long enough at this problem, you will also get that it simplifies to cos. And if you have nothing better to do, you can try it out yourself. The numerator, I know right now it doesn't look very nice, but really all it is, you just need to make a common denominator and then bring them together. So the top shouldn't be a problem. It should be something over something, right? The bottom, there's a lot of work to do, because what you can think about is you can trade out one of the either tan squared or the cotan squared for something, right? So then, like, I would say secant is an easier function than tan, or you can think about cosecant is an easier function than cotan, right? Because secant is just 1 over cos, and cosecant is 1 over sine, right? You can trade that out, and then you can eventually make a common denominator, okay? If I were you, and I actually did this, I would trade out both. So let me just demo real quick. Let me get my Pythagorean identities. Pythagorean nice.
Right, okay. So you have tan and secant, cotan and cosecant. Okay, cool. So what I would do here is that I would substitute, like for the cotan one, if I move the 1 to the other side,
then I know this bottom part becomes cosecant squared theta minus 1 minus,
what's tan squared? Well, tan squared is here. Move the 1 over.
so that would be secant squared minus 1, right? And you see how in the bottom here you have a minus, you have a minus 1, and then you're going to minus another minus 1, right? So then what that happens is such that, you know, this turns into, well, the 1's cancel out, and then you have secant squared minus, cosecant squared minus secant, right? So really what you have is you have, okay? So then that means all you have to do is make a common denominator, and then you can somehow collapse the bottom also into something over something, and then you divide by their fractions, okay? So if you really want to juice yourself up and try this question out, you could, okay? But obviously this would be a lot more difficult than just decomposing, okay? But that's kind of the thing with identities, is like you kind of need to see both to understand in the future what would be an optimal solution, right? You won't know until you try. So here's our try. Great. So I think that takes care of all of number 5. Yeah, have a go at it. Good luck.